So yeah, today I'm going to be talking about AIME geometry, and specifically this presentation is on circles. So yeah, there's a few things that are usually covered when we talk about circles. One of the things that probably comes to mind first is power of a point. So this basically says that if we have a circle and a point situated somewhere around that circle, like inside it or outside it, we define this notion of a power of that point to be if we have a segment or a chord of that circle with the point on it, then the power of that point, let's say P, is just going to be the product of the two parts of that chord. So the power of P is AP times PB, and it's also CP times PD. And we get that these two are equal, and that's true for like any chord passing through that point. And otherwise, if we have a point outside the circle, we can have a tangent, let's say at A, in which case we define the power to be PA squared. And then if we have like the normal setup, we have PB times PC is going to be the power. Yeah, so that's what power of a point is, and it's very useful. Another thing that shows up is like angles within a circle. So if we have a tangent at A, then let's say we extend this to B, then any point C on the circle here, for any point, C, we're going to get that this angle is equal to this angle. And the reason for this is if we draw this line such that we have a right angle here, then this fact is actually much more obvious because this dotted line is going to go through the center of the circle and it's going to be a diameter. So that means that the angle that we've labeled is equal to this other angle. I'm not sure if like the drawings I'm making are updating very well, but hopefully you can see it. Okay, well, yeah, those two angles are intercepting the same chord, so that means that they're equal, which is like an easy way to prove this fact. And then okay, my Wi-Fi is not doing well. Sorry about that. I am back. Basically what I said is that this angle is going to be equal to this one because they're both 90 degrees minus this blue angle. And then the red angles are both equal to this angle because they intercept the same arc. So yeah. And then another fact that's like you probably learned pretty early is that two tangents are always the same length, two tangents from the same point. And then finally, Just in general, like when we have problems with circles in them, a lot of the time it's going to be paired with either Pythag or like angle chasing or some kind of similar triangles and stuff like that. Okay, so this is just an overview of some things you can see with circle problems. And the rest of this is just going to be going through some problems that show this. So the first one, we have a quadrilateral that's inscribed in a unit circle omega. And we're given that AM is a diameter, so AM, and E lies on the angle bisector of RAM. So if we put R like somewhere here, then E has to be on the angle bisector. And we're also given that triangles RAM and REM have the same area. And from this, we want to find the area of MARE. So yeah, cool. I think we can probably just start solving it. Hopefully you've like processed the question and everything. But one of the first things that we can see is that RE equals EM, and that is because the angles RAE and EAM are the same, so the chords they intercept have to be the same length, which means RE has to equal EM. And the next thing we do is if we look at ARM, obviously this is going to be a right angle because AM is the diameter. And one thing that we can do is we take this midpoint of RM and call it N. And we know that since REM is an isosceles triangle, the midpoint of N, if we take that and connect it to E, NE is going to be perpendicular to RM. And also, we know that if we have the center O of the circle, OE is also perpendicular to RM because like the altitude from O to the chord RM is always going to intersect RM at its midpoint. It's basically ON is the perpendicular bisector of RM. So we have that ON and E all lie on a line. Okay. We also know that triangle O or ONM is, I don't know why I put O there. Sorry about that. O is on AM because it's the diameter. There, that makes more sense. Okay, ONM is similar to triangle ARM, and that's just because like ON is parallel to AR, which is also perpendicular to RM. And also like MO to MA is 1/2. So that's the ratio of these two triangles. We also know that AR is equal to NE because of the condition that these two triangles have the same area. Because the area of RAM is AR times RN, and the area of REM is Rn times NE. So canceling, we get this. And finally, if we know that the ratio between these two triangles is 1 to 2, then ON over AR is also 1 to 2, but this is also equal to ON over NE. And we're given that this is a unit circle, so O equals 1, which means ON is 1/3 and NE equals 2/3. From this, we find that the area of MARE is twice the area of MRE, which is equal to NR times NE times 2. And that is equal to 2/3 times 2 times NR. So NR is going to be 2√2/3 because if we use Pythag on triangle ONR, we know its hypotenuse is 1 and one of its legs is 1/3. So the other one is 2√2/3. So we get 8√2/9 as our answer. Okay, so that wasn't too hard. It was just a little bit of similar triangles and I guess dropping the altitude from O to E, or also like making the midpoint. Either of those is the same. Okay, cool. The next problem is this. It's a little bit different. There's a lot of like tangent stuff. So yeah, we have a rectangle ABCD, and we're going to draw circles in this rectangle. So if we have A, B, C, and D like this, we're given that BCDE has an inscribed circle, which means that it's like restricting how this is going to be able to look. So E is like here-ish. And we're given that this is tangent to BE at T. And then also ABE's in circle is tangent at T. And we want to find the ratio of the radii, the big one to the small one. Yeah. Okay. So for this one, it's pretty much just like drawing all of the lengths from the center of the circle to the points of tangency, and the rest of it is like not that bad. It's just like algebra. So if we call the radius of the big circle R and then the small one R, big R and small R, we also need, I think, one more variable. So yeah, we're just gonna kind of fill this out. So this side is 2R, and then we're going to have here 2 big R minus small r, which means that BT is also that length, and then this one is also that length, and then R here. Okay. And I think that means that we need one variable. So let's call this X, like this length here. And then ET and this length are also X because they're all tangents from the same point to some triangle or some circle. Okay, so now the only thing that we really have left to do is Pythag. So that's what we're going to do. I guess first we do know that r plus 2x is equal to 2r minus r. If we look at this red side and this red side, because it's a rectangle, which means that 2r equals to little r plus 2x. So big R equals r plus x. Yeah. And what that gives us is that we see AE is equal to r plus x and AB equals to big R, which just means that AB is equal to 2AE. So then EB is equal to square root 1 squared plus 2 squared times AE. So root 5 AE. But we also know that BE is equal to 2r minus r plus x. So this is going to be equal to root 5 times AE, which is r plus x. And then we can simplify this a little bit if we want to make r equal to r plus x. So big R is r plus x. We have this is equal to 3x plus r is equal to root 5x plus root 5r. And then solving, we're going to get that r equals, what does r equal? If I can't remember, I will just do it. It's fine. So that means that the ratio of r and x is going to be 3 minus root 5x is root 5 minus 1r. So r equals 3 minus root 5 over root 5 minus 1 times x. And that gives us root 5 minus 1 over 2 x. And then from here, we also know that r is equal to r plus x. So we're finding the ratio of r plus x to r, which is 1 over x plus r. Okay, so I actually did it backwards, but this is going to be equal to 1 plus root 5 plus 1 over 2. So that is 3 plus root 5 over 2. Okay, cool. Yeah, hopefully that was clear. And we will go on to the next question. So for this one, we have an isosceles triangle in a unit circle, again, ABC. Oh, that's not very nice. Okay. And what we're given is that we have this other point that is the reflection of C across AB. It's like here. And we know DO is equal to root 3, and the radius is 1. And we're trying to find the area of ABC. So for this one, there's kind of a few ways that we can do this. So one way is that by like reflection, we know that this angle DBA is equal to CBA, which is also BCA, because the triangle is isosceles. And we know that this angle is then this angle. And if you recall from the thing at the beginning, that means that dB is tangent to the circle omega. Okay. And this is helpful because now we can use power of a point. So we know that BC is equal to BD. And having BC is helpful because that'll help us find the area of the triangle. So BC equals BD, but BD is equal to the square root of the power of the point D. And one other formula that I forgot to mention is that the power of the point is equal to the distance from the point to the center squared minus the radius squared if that point is outside the circle. So we can prove this pretty easily by just like writing out the lengths, but I will not do that right now. So that gives us OD squared minus R squared, which is just 1 squared. And OD is equal to root 3, so this is square root 2. Cool. Yeah. That means that if we drop the altitude completely, each of these lengths is root 2 over 2, but also BO is 1, so then this is just an isosceles right triangle. And we're going to get that the area of ABC is equal to root 2 over 2 times 1 plus root 2 over 2, which is root 2 plus 1 over 2. And for this problem, if you assume that ABC is acute, this is what you get, but you could also get root 2 minus 1 over 2 if you assume it's obtuse, which the problem forgot to include, but yeah. Okay, cool. So apparently these take slightly longer than I thought. Let's see. I will probably have time for only one more. So I'm going to see which one I want to do. Okay. Let's just do this problem. So we have two circles. Oops. And their radii are given. Oh no. Okay. And we also know that they're tangent to each other. So that's not that bad. Okay. And we're asked for the largest possible area of a right triangle where all of its vertices are on one of these circles. So first of all, if we consider like some cases, the triangle's vertices can be on like either of these circles, and if we let the hypotenuse be on just like one of them, like both of the vertices of the hypotenuse is on one of them, then the largest possible area we can get is just a 45, 45, 90 triangle. And in that case, the area is just going to be r squared. So we're going to see if we can try to do better than that. And intuitively, it makes sense that the best we can do is going to utilize both circles. But yeah, if we have the two endpoints of the hypotenuse on different circles, let's say like these two, then we also know that this is a right triangle. We also know if we say this is O and then ABC, the distance from O to AB is only half of the distance, or exactly half the distance from C to AB, which is a leg of the triangle. And that is because we have these isosceles triangles here. And then also like this altitude is perpendicular to BC, and AB is also perpendicular to BC. So that means that these two lengths are equal. And yeah, so the altitude from O to AB is like this length, and then from C to AB is just twice that. Which means that in order to find the area of ABC, we can also just do twice the area of AOB. And this is equal to OA times OB times sine the area, or sorry, the angle between those. Okay. And actually in this diagram, it's like pretty close to optimal. But the way that we want to maximize this is, first of all, OB is fixed because it's just going to be 100. We could also make it 71, but that would not be as good. And yeah, if we have AO and AOB as the only variables, the largest that AO can be is 71 plus 71 plus 100, because we're taking the distance from one point on the first circle to the center of the second one. So the biggest that can pass through each of them is like twice 71 and 100. And then the largest that the sine of an angle can be is just 1, and that happens when this angle is right. So that's like kind of what it would look like if we had the optimal triangle. And if we evaluate this, the answer is just 24200. Yeah. Okay. I have like a little bit of time, so I think I'll just kind of give like part of the idea for this last problem. So we have this triangle ABC and the midpoint M, and then we also have its orthocenter H and its circumcenter O. Yeah. And we have this point that's the reflection of M over H, but this diagram is like terrible. Since we're given that OA equals ON, which is the radius of the circle, that means that N has to be on the circle, which is, yeah, okay. And then each of those is 7, and then OH is 11. And we're asked to find BC squared. So the way we do this is like, one thing we can notice is that we have this reflection of M across H, but if we reflect H across M, we also get a point on the circle. And this is because basically we can do some angle chasing. We know that like this is going to be equal, and then we also know BM equals MC. So what we get is BHCH prime is a parallelogram, and then that gives you like the angles of it. And then we can also find angles like involving A. So what you end up getting is that this angle and this angle add up to 180 degrees, which means H prime has to be on the circle. But anyway, once you get that, if we take the midpoint of HM, then we're also getting the midpoint of NH prime because everything is split evenly. So, like, we can find BM using Pythag, and then like we can also find that OM is equal to 7, and that's what enables us to do that. Yeah, and then OB is also 11. So then you get BM, and then you get BM squared, or BC squared. Okay, cool. Yeah, I went a tiny bit over time, but also like there's this problem that I was told to give. So I guess this is like homework-ish. And then there's going to be a recording of me like going over the solution sometime later. Yeah, okay, that's it. Thank you.